Right, hello, and greetings, minions. I hope everyone's having a lovely day. I know I am, because it is actually warm and sunny and gorgeous out, and it's been really lovely. I hit about 26 today, which is a very nice change from what it was. And as we all know, we are essentially plants. We need to hydrate, and we need sunshine, and we're finally getting some of that. So, anyways, this has me feeling pretty good, and so I figured I would come on and do a stream tonight. I'm a little on the late side, but I was just feeling like doing some chemistry because I'm an enormous nerd, and never forget that this is in fact fun for me. This is not in mockery of people who struggle with chem. It's just Oh man, sometimes I run out of words and then I take a drink of water to try and pretend I didn't. Hi, Callisto. But yes, anyways, chemistry's fun. And so there's... I'm not going to do a very long stream today, but I'm going to work on some questions. And just some questions from a problem set that I was looking forward to doing, and if there's one particular friend that shows up in chat, there's a different subject I want to tackle, particularly concerning orbitals and just what the heck those are, and how we just like the fundamentals of how we define those and how we fill them and use them, and how that you just build upon that foundational knowledge until you get to a point of looking at, I don't know why I'm pointing at the screen, don't mind me, but it's just building on the basics until you can relate the fundamental principles to the kinds of questions that we tackle, and use that to rationalize what's going on, so it all makes sense, because it all does make sense, because everything in chemistry gets made fun of a bit, mostly by chemists, because all of our rules in quotation marks, are like we say here's your list of rules, and here's your lists of exceptions to that rule, and that's true to some extent, but that is just because generally in day-to-day chemistry, and in the entirety of most like undergraduate curriculums, look at me using a bad plural as curricula. Anyways, the rules that we teach and that we use in most of these problems are oversimplified. They are there's approximations made. There's little fudge factors we introduce, or there's complexities that we ignore because they don't make that big of a difference in practical terms. So it's like it's an accurate enough rule for most cases if you keep the exceptions in mind. But the thing to realize is that there are not exceptions to the fundamental rules. None of these reactions, none of these chemical interactions break any laws of physics or anything. So they are all following the rules. Even the exceptions are following the rules. It's just more complex and deeper rules than we tend to invoke when we're going through these. But Anyways, yeah, so that's my little rabbit trail for right now. I'm sure we'll get into some more later. So I do. There we go. There's my screen. Okay. Okay. So last day, we started off by just drawing some structures. It was taken from the not the systematic names, the trivial names, and the structural formulas, just to draw out the structures that we were talking about. And then I think we just kind of abandoned that entirely, because we just started talking about like what chemical reactions are, which is always the reorganization of electrons between compounds or within the same compound. And so we just kind of went from like the precursor to talking about all these reactions to talking about like what is a reaction. And so we went back and we talked about just like what is happening with orbitals, because electrons live in orbitals, and there's room for exactly two of them in an orbital. You can have empty, partially filled, or filled orbitals, so with 0, 1, or 2 electrons. And chemical reactions happen when a orbital with at least one electron reacts with an empty orbital, or in the case of a 1 electron reaction with another orbital that has 1 electron. But always a maximum of 2, hard limit. So full orbitals do not overlap with other full orbitals, because that would introduce extreme electron-electron repulsion, and like the other 95% of chemistry, it is all about reducing electron-electron repulsion. And so, yeah, we were talking about orbitals, we were talking about atomic orbitals and how those get combined into molecular orbitals, where if they're the same phase, they act like 2 bubbles meet, and then they just sloop up into one bigger bubble, and that's a bonding interaction that holds molecules together. That is what a bond is. And then if the orbitals are of opposite phase, or if there's a phase mismatch between the 2 orbitals that are overlapping, then they act more like balloons, where you can push them as hard as you want together, but they're not going to combine into into one cohesive orbital. They're going to push up against each other. They're going to squish around. They're going to change shape in response to the proximity of the others, but they will never combine. And there is they introduce what's called nodes, which is these little, represented by that little dotted line, where there's this space, this border, basically, where there's 0 electron density in that space that is between these 2 phases of these 2 orbitals. So, what I'm going to do today, which I'm pretty sure I already said, but I'm going to say it again, just more to keep myself on track than for any of your sakes. So I'm going to just start answering a couple of these questions, talking about types of reactions, and then if my good friend comes around, then we can talk some more about orbitals, because I really want to get into kind of some of the more fundamental bits of what's going on. So I'll start with these. So SN1 and SN2 reactions, these are nucleophilic substitution reactions, and so it's something comes in and combines with something else, and the substitution part is that when it comes in to form a bond with a new compound, it kicks something else off. So something attaches and something detaches. So that's the substitution. And there's a lot that we can do with these. So these all require the interaction of a nucleophile and an electrophile. So nucleophiles are essentially like atoms, or like we refer to like entire molecules as nucleophiles, but really it's just a particular site on a molecule that has a large amount of electron density. So this is very common. I think things like so you can use things like an OH group is not a particularly good, like it's not a very strong nucleophile, but it can be used as a nucleophile because it has these two electrons around it. Well, four really. These two lone pairs, and those are electron density that's kind of concentrated on the oxygen, and those aren't involved in any other bonds, and so they're available to be shared by the oxygen. So this can act as a nucleophile, but there's degrees to the quality of a nucleophile, and so if some general base B, this is not a boron with a lone pair. This is just some kind of base comes and plucks this hydrogen off of the alcohol here. Then the electrons in that OH bond go to be localized on the oxygen, and now this oxygen has three lone pairs on it and a fully negative charge on it. So it has a negative formal charge. So this oxygen has an excess of electron density. So like this one can be a nucleophile, but this oxide, the negatively charged oxygen, is a better nucleophile. And electrophiles are the same and opposite. Electrophiles are regions in a molecule that have like a lower density of electrons. I don't want to say like a deficiency, because that can imply that it has like less than an octet, which is not always the case. It can be, and that certainly would be a good nucleophile when you've got an atom with less than an octet. But electrophiles are not necessarily electron deficient, but they may have kind of a decreased electron density. And I'll show you what I mean here. So if we have something like, I know what to do. So we've got a carbon, and we've got, what should we do for this actually? Good prep. Okay. So we've got carbon here connected to let's just say three other carbons. It's a T-butyl group. So bromine has the greater electronegativity, and I'm going to draw out the electrons on bromine because it's neutral. But bromine has a greater electronegativity than carbon, which means that it pulls harder on the electrons around it than the carbon does around itself. So the bromine has a stronger pull on the electrons that are between the carbon and bromine, that are shared by the carbon and the bromine. So the electrons in this bond are being pulled on by both the carbon and the bromine, but pulled on harder by the bromine. And so this kind of the chemistry term is this polarizes the bond towards bromine. So the bromine actually pulls the electrons in the bond closer to itself, and this produces like this partial negative charge. So this is the Greek delta symbol. So it's just the symbol for having a partial charge, not a full charge. Like this oxygen here has a full negative charge on it, whereas this bromine has only like a slightly negative charge on it. It's very small, much less strong. But by the same token here, the carbon then has a partially positive charge. Because it must, because we always have to maintain charge neutrality with anything that we do, because unbalanced charges, they're sort of not a thing. And when they do become a thing, they very quickly correct themselves. And so, like, think of like lightning, where you develop charge separation between the ground, or like a big metal pole on the ground. There's a charge separation between that and the clouds, and so that quickly gets corrected by lightning. So yeah, charge separation. Yes, we do see it sometimes, but it is it is something you have to force and put energy into maintaining. Anyways, that seemed like a bit of a tangent, but that's okay. So so this is an electrophile. This carbon here, because its electrons are being pulled away from it by the bromine, so it reduces the electron density on carbon. So this is an electrophile. But, oops, I always kick that. Okay. Well, let's say we've got a similar compound. Not really that similar, but let's call it... I'm pretty sure I'm just making this molecule up, but it's a thing that doesn't break any rules, so so we're just going to go with it. I'm going to be a good little chemist and put all my lone pairs on. I hope my professors are proud of me. I'm just kidding. I know they are. That was my attempt at being wholesome. It will not happen again. Okay. So, now, this carbon is still attached to the bromine, which is still pulling slightly harder on the electrons in the bond than the carbon is. So the carbon develops a partial positive charge, but the fluorine is also pulling very hard on the electrons in this bond, because fluorine is significantly more electronegative than even bromine. And so they are pulling proportionally harder on the electrons in the bond around carbon. And they are all doing this at the same time. And that means that this carbon has a really large partial positive charge. It's still not a full charge, although this may approach it. I don't know. I would have to do some calculation, some computational work to see what this would actually be like. But so this is a much more partially positive carbon than this one up here. So this is a better electrophile, and you can have. Actually, oh man, what I should have done first is if you have. So let's say you got this compound. And one thing that can happen, and particularly something that can happen in an SN1 reaction that we will be going over shortly, is you can just have this bromine just fully take all of these electrons and just go off on its own. It'll just leave and take its electrons with it, and that produces what's called a carbocation. And so this is a carbon with a fully positive charge on it, and this is actually electron deficient, because this carbon only has 2, 4, 6 electrons around it in its valence shell. So this is a carbon that is short of an octet, and as a result, it is now like an extremely good yes, there we go. It's an extremely good electrophile because it desperately wants electrons. And so these carbocations are extremely reactive because they will they will collect electrons from wherever they can, and just in order to form that stable octet and just stop being so naked. So yeah, decent electrophile, better electrophile, amazing electrophile. So that's what we're working with. We're working with nucleophiles and electrophiles, and they come together. They redistribute this electron density so that the electrons are more spread out, and then that's just the more energetically favorable state to be in, and so that's what everything tends towards. And congratulations, now you can do 98% of chemistry. Probably. All right. So that was a lot of talking before I actually got to. Now I've taken up all my drawing space. So I'm going to actually erase those because I think we can remember the points that we've got nucleophiles and electrophiles. They react together, and yeah, I think we're okay. Yeah, okay, good. All right, so what we got here. Is this? So we got a 5-membered heterocycle here. Just got an oxygen in the carbon ring. So the things that we have available I'm going to try that again. So the things that we have available to us in this reaction here are this molecule, the starting material, and we've got HBr. So we've got a strong acid. Yeah, we're not told what the solvent is. So generally we'd assume water. I mean, pretty much always we assume water because that's what HBr would generally be kept in. I don't remember off my head the molarity of hydrobromic acid. It's quite high, and it's extremely acidic. Wicked stuff. But anyways, the important point is this is a strong acid, and we've got a lot of it. So generally, when you're approaching reaction questions or like this kind of question where you're like, hey, so we need to draw a mechanism, so we need to know what is reacting with what. If you're given a strong acid, chances are your first step is going to be it protonates something. Because like HBr very strong, particularly a Bronsted acid, which is to do with hydrogen transfer. So strong acids really like to give away hydrogens and you kind of force them onto other atoms. So that is pretty much always what we're going to do when we've got a strong acid. Okay, so the first thing that's going to happen. So what is it going to react with on this molecule? We've got carbon, hydrogen, single bonds all over the place, and then we've got an oxygen with lone pairs. And really here there's only one option because there's only these lone pairs that are not already involved in other bonds. Now this comes with a bit of a caveat because sometimes we can use bonds as a source of electrons. And we're actually going to see some of those in question 2 down there, which is this one here, where we have alkene addition, pardon me. But it's very difficult to use single bonds as a source of electrons for a reaction. So there's probably cases. I'm struggling to find one though. Like you have to have some very strong motivation to start using single bonds as electron sources, unless it is to avoid breaking an octet rule, and we'll get to that later, probably. So, by a very large margin, the most reactive electrons on here, and the actual the nucleophile of this molecule is the lone pairs on oxygen, and so that is going to react with the strong acid. So we always have the Bronsted base is going to attack the hydrogen of the Bronsted acid, and that is always going to be the order we do things in. We always draw arrows from electron source to the electron target. So when the oxygen attacks the hydrogen, this bond must break because a hydrogen can only tolerate 2 electrons, and so like one single bond. So if you form a bond to the hydrogen from the oxygen, then you have to break the other bond, and because it cannot carry both of those bonds at the same time. So this produces, let's do blue. We are good. All right. So now we've got okay. So now what we've got is this positive charge on oxygen, because now it has. If we're counting for a formal charge, then we split each of the bonds in half. So each bond counts for 1 electron, and the lone pair, of course, counts for 2 electrons. And so this is what is it? Valency minus electrons. I'm just going to abbreviate by E minus. So the valency of oxygen is 6, because oxygen has 6 protons in its nucleus, and so in order to be neutral, oxygen needs 6 electrons around it. And so there's a couple of definitions that kind of clash here. So this oxygen has a stable octet because there are 8 electrons in its vicinity, which is an awkward way to say it, but I'm going to stick with it for now to make a distinction. So when we count each bond as 2 electrons, because these are 2 electrons that are shared between 2 atoms, that's what a bond is. And so we count up 2, 4, 6, and then the lone pair makes 8. So the oxygen has a stable octet. So it's got it's a noble gas configuration because it's got a full octet. But when we are assessing formal charge, that's when we do the valency minus electrons. And when we count formal charge, we only count 1 electron from each bond. And so in this case we have 1, 2, 3, 4, and 5, because the lone pair counts for 2. So 5 equals 1. And so this has a +1 formal charge. So the next thing we can do with that, what else are we doing? Okay, so there's actually only one way that we can do this one. Okay, so what happens here? No, there are 2 ways to do this. Okay, so yeah, I'll explain that in a minute. So we'll just go into one way to do this. So we've got this compound, and now what we've got in solution is we've still got HBr, because we were told we've got excess. But we've already protonated something on here, so it's not likely to be protonated twice. It's in fact incredibly unlikely to be protonated twice before we do anything else. So yeah, the general rule of doing acid-base chemistry is proton on, do a thing, and then proton off. Because we don't put multiple charges on on a molecule while it's reacting unless we have a very good reason to do so. So there's two ways to do this. No, I already went over that part. But the other thing that we've got in solution here is bromide. So the Br minus that's left over from the molecule of HBr that just reacted. So I kind of want to see, can I just like move this ever so slightly? Why is that little ghosts of stuff that was like, that's strange. Okay. How deep we got settling? Okay, so two ways we can go, and I'm going to color code these as best I can. So one way that we could do this is by breaking. Whoops! Stop that! I'm so good at this. Oh, and I cut off my bromine. Just gonna do it for one moment. There we go. Okay. So there's two ways we can go about this. We can either break this bond, and the electrons will go to oxygen because oxygen is the more electronegative of these. Between oxygen and carbon, oxygen is more electronegative. So when the bond breaks, the electrons go with oxygen. And if we do that, what we form is this, and let's see, 1, 2, 3, 4, 1, 2, 3, 4. So now we go to the OH. Okay, so this formerly positive oxygen took electrons from carbon, and so now it's back to 2 bonds and 2 lone pairs, which makes it a valency minus electrons of 6 minus 6, and then that means that oxygen is now neutral. So you push electrons towards a positive charge, you neutralize that positive charge, but you move electrons away from a neutral charge like that one, and you form a positive charge. So now again we've got this electron deficient carbon, this carbocation, and so this ring has broken now, and well, whatever can we do? Well, we've got a bromide, a Br minus, which functions as a pretty good nucleophile, and will react with that carbocation. And that forms and let's call you the bromine. Very good. Okay, so we formed a carbocation, and then the negatively charged bromine just came in and attached there because the negative charge can balance out that positive charge, and everybody's neutral, everybody's happy. So, but we're not done yet, because we've made this part of our target molecule. So we broke open the ring and we attach a bromine to that tertiary carbon there. But now we've still got this OH group attached, and we need to replace that with a bromine. So how do we do that? Well, we're going to take some of that excess HBr that we have still sitting around because we were told that we do. And the oxygen is going to get protonated again. What am I looking for? I'm looking for... Oh, nothing. Got it. Okay, so that makes... I'm going to draw it over here because I'm feeling whimsical. and it doesn't matter. These are perfectly equivalent. These are the same molecule. So we've got oxygen with one lone pair now, and two hydrogens attached. And this bond, this oxygen now has 3 bonds and 1 lone pair, which is, once again, a positive formal charge on the oxygen. Now, we cannot pull the same trick as we did in the first reaction up here. Where we had a positively charged oxygen and we just broke a bond in order to give it electrons. We cannot do that here, and this is the reason. When we did it up here, the carbocation that we formed is tertiary. So it means it's a carbon that has 3 other carbon groups around it. And when that's the case, so you've got this positively charged carbocation. It's a very unstable thing. It's very difficult to form because it's extremely unstable. And the hydrocarbon groups around around a tertiary carbon kind of insulate that charge a bit because they provide like this cushion of electron density for the carbocation now to pull on, because it's very deficient in electrons. It has this unbalanced charge. It's got more positive charge from its protons than it has negative charge from its electrons, and so it is looking to pull electron density in from anywhere. And so just like when we were talking about what electrophiles were before, now this carbon has a fully positive charge, and so now it is going to pull very, very hard on the electrons in the carbon-carbon bonds around it. And so that is going to offset this fully positive charge with this partial negative charge on that carbocation. Now, to be clear, this still has an excess of positive charge, or I should say a deficiency of electrons. This delta minus does not fix that this is a carbocation, but it makes it a little bit less bad, because one of my professors always told me nature abhors a focused charge. And so anything that you can do to spread charge out, be that charge positive or negative, doesn't matter, anything that you can do to spread that charge out or make it less bad is a good thing. And so this carbon becomes a little bit less positive because it pulls on the electron density of the carbons around it, making them slightly positive. And so there's always this push and pull of electron density. And yeah, so we're always just trying to avoid these big focused charges. So the reason that we cannot do that here is that if we were to take the electrons from that carbon-oxygen bond and just give them to the oxygen, we would be forming a carbocation, but it would only have 1 carbon group to pull on, and so it would have like still a delta minus, but a really small one. So there are also hydrogens around this carbon. But the thing with hydrogens is that they don't really do anything to stabilize a carbocation, because hydrogens only have 1 electron. All they've got is the electrons that are in the bond between the hydrogen and the carbon. So those don't offset this carbocation by any more than a negligible amount. So this is a far less stabilized carbocation. And so it's simply just not going to form. You effectively cannot form a carbocation at a primary carbon, a carbon that is only attached to 1 other carbon group. And it is for this reason. It would be a much more focused charge, and that is disfavorable, energetically speaking. Take my bad arrows out. And I'm going to take those hydrogens out too, because they're about to be in the way. Okay, so now we cannot just break this bond arbitrarily, but we're going to do it anyways. But what we have to do is provide it with a little more motivation. And so just up here, we know that there is more bromide around because we just used another molecule of HBr to protonate that alcohol. Hello, Daphne. How you doing? Come here. Hello. Hi. Here's one. So, so we know that there is Br minus, a bromide, in solution because we just made one. Excuse me. And as we said before, bromide can act as a nucleophile. And so what we can do, instead of just giving these electrons away, is the bromide comes in and attacks this carbon and simultaneously kicks out that protonated oxygen. And now I'm doing it in purple, but that's fine. Electrons could be purple too. And so when that happens, there's no consistency with my arrow colors anymore. We're just abandoning it. 2, 3, doot. Now bromine is up here. And so now this has become a bromine as well. So now we are actually done because this is the target molecule now. Looks a little bit different, but I could have just as easily drawn this bond going that way. Yeah, so these are the two different nucleophilic substitutions. This one is SN2, and it's SN2 because in the rate determining step, there is two molecules interacting. There's a bromide interacting with whatever the hell this is. And this is the rate determining step because this is only one step. So this portion here, from here to here, was an SN2 reaction. We had nucleophilic substitution on that carbon. We substituted a bromine in and kicked out this oxygen, hydrogen. Effectively, this is a water. It kicks out just neutral water. Boop, 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 boop. Okay, and that means that this section up here so this was, oh, actually, I shouldn't, so actually, it's just from here. This is an SN1 reaction. I did not include this step because this is just an acid-base reaction. This is just protonating the oxygen, and this was necessary to do the nucleophilic substitutions, but this is not part of the nucleophilic substitution reactions. Yeah, so this is SN1. The 1 means that in the rate determining step there's only one molecule that reacts, and so that is this step here, going from this molecule to this one, because in this step we form the carbocation. We break this carbon-oxygen bond and we form a carbocation, and that, as I said, that is an extremely difficult thing to do. It's very energetically expensive, and as such it is slow. And so in an SN1 reaction, the rate determining step will always be formation of the carbocation, and there's only one molecule that is reacting in this step. It's just this one breaking a bond within itself. Alrighty. I feel like there was something else I wanted to say. Give me a moment to think about that. Can't think of what I was going to say. Alright, well, that's going to bother me for a while, but I'm not going to worry about it too much. If it turns out to be important, I'll generally bring that up on the next stream. Be like, hey, I I was dumb at this point, and here's what I did that was dumb. I don't mind doing that. Oh, right. Of course, I remember what I was going to say. All right. Okay, so I said that the order you do these steps in isn't important, and let me show you why. Or at least part-wise. So, at this step, so same step happens here. We just protonate the oxygen in that ring. You got a hydrogen and positive charge. Okay, so the other thing that we could have done is essentially it's doing this step first, doing the SN2 reaction before the SN1 reaction. And, sorry, I've got a crunchy neck. So in this step, we broke this bond in order to neutralize the oxygen. But we could have also done this in order to neutralize the oxygen. So we do the SN2 reaction first. So we have this, a nucleophile attacks the electrophile and simultaneously kicks out a leaving group. And that is one thing I really didn't discuss at any length, but that is okay. We're not going to go over that today because I don't feel like it. I'll do it probably next time, I would imagine. Anyways, let's not go writing checks that I may not feel like cashing. So we did the SN2 reaction first. So this is the only step of the SN2 reaction. There are two molecules reacting in the rate determining step, which is the only step. So this is also perfectly viable. And in fact, this is probably the more likely route because SN2 reactions are intrinsically faster than SN1 reactions by a lot, by 100 to 1,000 times. It depends on factors that include how strong is your nucleophile. Remember, you could have different strengths of nucleophiles. Things like so how strong is your nucleophile? How strong is your electrophile? And how sterically crowded is the carbon that you're doing chemistry at? Because if things can't physically reach the reaction site, or if they can only approach the reaction site from a very particular angle, that slows it down because it will happen statistically less of the kind of attempts, because these are all just molecules bumping together in solution. There's no direction of these, no mushing together of the reactive stuff. They're just bouncing around in solution randomly and in random orientations. So steric crowding around the kind of active site, the reactive site, can influence the speed of reactions. But all else being equal, SN2 reactions are much faster than SN1 reactions. So this is actually likely this is the more likely reaction route, is to do this step first. Anyways, I'm going to stop saying the same thing 4 times and move on with this. So, 2, 3, 2. Now you are the OH, and you are neutral because again we pushed electrons towards a positive charge, so we neutralize it, and we took electrons away from a neutral charge. So that would make it positive, except that we had a negative charge coming and attacking that, so everything is offset. So essentially, we're taking electrons away from a negative charge, which neutralizes that. We're kicking electrons out from this carbon, so it doesn't change because it's getting attacked and also releasing a bond at the same time. And then we got electrons going towards this positive charge, which neutralizes that. All right. Okay, so we end up with kind of the opposite case that we had in the other route, but essentially it follows the exact same kind of reaction pathway in that now we're going to protonate this oxygen because we were told that we got excess HBr. Cancel that. So let's see. So that turns into OH2 plus 1 lone pair. And bromine with 3 lone pairs. Okay, and so yeah, so let's circle these again. So this was our SN2 reaction, and then we're going to follow that up with the SN1 reaction. So this is again like an OH2 plus, and so we're going to take electrons away from that carbon, which makes it a carbocation, and we're going to push the electrons towards that positive charge, which neutralizes it. So then we forgot your doot cation. And then of course we made water as well with that. You don't have to include these usually unless you're asked for them. Wow. For completeness, there it is. So now we've also got, of course, a bromide in solution. So this can act as a nucleophile. Now, technically, I hear you saying that, but wait, couldn't the oxygen act as a nucleophile as well? And yeah, absolutely, it certainly could. And I would bet you that a significant portion of the time, that is exactly what happens. When you kick out the water from this carbocation, there's probably a significant amount of the reactions that happen are the water going back and attaching to the carbocation again. Which all that does is it takes us back a step, and then this happens again, and you get another kick at the can. So yes, this happens, but it doesn't get us anywhere. So it's a perfectly valid, important thing to realize that you know this is a possible reaction, but this is a reaction that just gets you stuck in a loop of associating and dissociating. So the way to drive this reaction forward is to attach the bromide, and like this is yeah. So like these loops here with attaching and detaching the water, they don't go on forever because some percentage of the time the Br minus will act as a nucleophile instead, and then the reaction stops, and we stop oscillating back and forth between these. So I'm just going to be lazy and draw an arrow up to that, because that's what we've just made. So yeah, there's two perfectly valid ways to get to that answer. It just depends if you want to do the SN1 or the SN2 first. And this is, of course, the SN1 reaction. Alrighty. So one final pretty nitpicky point. Oh no, actually no, it's completely valid. Forget it. I never said anything. No points at all. What I was going to say that I'm wrong about. Caveat. Disclaimer. There we go. That's one. So I was going to say, oh, but we may not have just Br minus floating around because we weren't told. So like the very first time that this would happen, we don't necessarily have that. Which my answer, there definitely can be situations like that, because you could have something like reacting this with H3O plus and sodium bromide, for example, where like you could just add Br minus but not have this reaction happen, or not have sorry, what am I even saying? No, I'm thinking completely backwards. You ever get those times where you wish you could just erase the last 30 seconds because you're saying something completely wrong, and this is your sign to yourself that you should probably be done streaming and trying to sound smart pretty soon. So I'm just going to finish explaining what I actually meant, and then I am going to bounce. So let's take that off because I'm pretty sure that's not relevant. So if you had just HBr in solution, you might say, oh, but there's no Br minus yet because the HBr hasn't reacted. To which I say, well, it did though. That was the very first thing that we did, which completely validates everything. But if you had a situation where it was like that, you could say, yeah, maybe because there could be even things like if you had this being an OH minus. So you had, but let's say you started in neutral water. If you've got oh god, what am I doing? Okay, so there is in pH 7 water, completely neutral water. There is like one part in 10 to, is it 14 or 7? No, 7, I think. One in 10 to the 7 molecules will be an H plus and OH minus pair, because of what's called the autoionization of water. So there's just if you just have water molecules just in solution bouncing around, just being water, being little guys. Sometimes they'll bounce into each other with enough energy that they react. An oxygen attacks a hydrogen and pushes electrons up onto onto that water's oxygen, and then this forms HO minus and H3O. Oh, I'm supposed to draw these out, silly boy. Okay, so this forms an OH minus up here and an H3O plus down here. And so like there's no such thing as as a solution of water, even when it is perfectly neutral water, there is always some ions present because of reactions like this, and like the H3O plus and OH minus will quickly react with each other. They're more than happy to do that, and that just restores 2 molecules of water. So this is constantly happening in solution, and so even if it was a case that you're like, oh, but if you got a situation where you don't have this somewhat nucleophilic Br minus, yeah, but you've got stuff like this happening, and so you still have access to these charged species, with a gigantic caveat that some things have a lot stronger bonds between them than water. But anyways, this has become a little bit strained, because I'm a sleepy boy. So I am going to sign off now, but I have enjoyed doing this one question. Just like taking an hour to talk through what is. I didn't even cover like a whole lot, because there's you can teach entire courses on nucleophilic substitution. People have written volumes about nucleophilic substitution reactions and all the different kind of types of reactions and reagents that you can use. and like what goes together and what doesn't, and like ranking all these nucleophiles and electrophiles and all these sorts of things. So this is a really big topic. I have barely scratched the surface, even taking an hour to do one mechanism. But with that, my brain is fried, and so I'm going to go and just melt into a little puddle. And I hope you all have a lovely night. Be good. Have fun. Be safe.